not going to break down that easily. Even though this is spontaneous. But you have to get to the transitional state first before the reaction goes forward. You add sucrase to the solution, it happens much more quickly. Because now you don't need that much heat from the environment for this to happen. Room temperature is good enough. So far, so good? All right, one question. What does the enzyme do to the delta G for the reaction? Is there a difference between the delta G here and the delta G there? No. The enzyme does nothing to the delta G. It only affects the activation energy. So I'm going to show you two more diagrams that basically go over the same thing. One is for an exergonic reaction. Enzyme lowers the activation energy, does not affect the delta G. And here's one for an endergonic reaction. Enzyme lowers the activation energy, does not affect the delta G. So delta G is not affected by the enzymes at all because your substrates and products haven't changed. It's the same substrate, same product. The only thing that matters is that the enzymes lower the activation energy, so more and more of the substrates can actually reach the energy level of the transitional state. There is enough heat in the environment to allow them to reach this, but very few of them will actually absorb enough heat to get to the transitional state in the absence of the enzyme. So the reaction will be very slow without the enzyme, but a lot faster with the enzyme. So how do enzymes actually do this? So remember, enzymes as proteins, three-dimensional shape, they could have tertiary structure or quaternary structure if they are made up of multiple polypeptides. And they have what we call an active site, a specific region in the protein, the shape of the protein where the substrates can bind. And then the substrate binds there, it actually causes what we call an induced fit. So the protein shape changes around the substrates, and then as it goes forward and the products are released, the enzyme goes back to its original shape. So the enzyme does not change. It might change momentarily, but then it goes back to its original shape. So how does it help? Why is it that bringing these things in the active site makes them react faster? Well, there are a few ideas. If you have the substrates in the solution, they have to randomly bump into each other before the reaction will go forward. If they're bound to the enzyme puts them together in the right orientation for the reaction to go forward, so the chance of them reacting will be higher. So it's the orienting the substrates correctly that might help. By twisting the bonds of the chemical bonds of the substrate as the shape of the enzyme shifts around the substrate, you might be straining the substrate bonds and bringing them into the high energy transitional state so that it's easier to break and reform bonds. The enzyme might be providing a favorable microenvironment. So in the solution outside, you might have a different pH than you actually get in the active site. You might have additional ionic charges in the amino acids of the active site that cause the substrate to react better. So all of those microenvironmental changes in here in the active site compared to the outside solution that might favor the reaction to go forward. And sometimes the substrate actually transiently, covalently binds to the enzyme itself, to one of the side chains of one of the amino acids of the active site. And then as the reaction goes forward, that particular amino acid side chain is restored as the products are released. So you actually do have covalently bonding to the substrate for some of the R groups of the amino acids in the active site. And I think this last one is not mentioned in your textbook. But you have to remember, covalently bonding and then releasing, so the enzyme always goes back to its original shape and its original form. So yes, the R group bound to a substrate, and then when the reaction is completed, the R group is released again. So far, so good? Question?
So what types of bonds besides covalent
Very good point. So how does the substrate bind? Usually you're looking at hydrophobic interactions and partial charges, hydrogen bonds, as opposed to covalent bonds. Covalent bonds are known for some reactions, not necessarily for all of them, and it would be binding to specific R groups of some amino acids. Other questions? Yes, sir.
Would it be polar or non-polar with
Very good question. That depends on what you're bonding to what. So remember, if it's a carbon-hydrogen bond, it will be non-polar. So we're going to start talking about environmental factors and how they affect enzymes. So temperature and pH are the typical environmental factors that might affect the shape of the protein and therefore affect the activity of the enzyme. And there might be specific chemicals that influence the enzyme as well. And so in a few weeks, we're going to do probably a 3-week-long lab that will focus on enzymes and inhibitors of various enzymes. So let's take a look at temperature. The left graphs here. For any given enzyme that you study, you always have what we call an optimum temperature. So that's the temperature at which the rate of reaction is maximal. So if you take a look at this graph, on your x-axis you have temperature, and on your y-axis you have the activity of the enzyme. So you're measuring enzyme activity as temperature is changing, and it's peaking at a specific temperature. That's the optimal temperature. Above that temperature or below that temperature, the rate of reaction goes down. So as you look at colder temperatures, why is the rate of reaction lower? Yes, sir. Because the collisions of the molecules is lowered because you have less heat available. They're not reaching the transitional state as much. So colder temperatures, fewer molecules reaching the transitional state, the reaction is slower. What happens with higher temperatures? Well, the faster the better. They reach the transitional state. You're kind of on the right track, but not exactly. Yes, sir. Why would the reaction stop? Why would the enzyme change shape? Yes, the enzyme would change shape. Why? Yes, sir. Which bonds of the enzyme would be affected by temperature? The hydrogen bonds are the weakest bonds, and as soon as you provide a little bit of heat, they might start breaking. And if you start breaking the hydrogen bonds, that could affect the shape of the enzyme. And as the shape of the enzyme begins to change, it's no longer optimal. And at some point, the reaction goes down to zero because you've so changed the shape of the enzyme that there's no reaction happening at all. So at that point, we're talking about an enzyme that's what we call denatured. Totally lost its shape, can't function at all. Now, different enzymes have different temperature ranges and different temperature optima depending on which organism you get them from. So in humans, what would you expect to be the optimal temperature for enzymes in your body? 37 degrees Celsius is your body temperature. You would expect the enzymes in your body to work optimally at 37 degrees Celsius. Otherwise, they would be working optimally. And if you look at human enzymes, this is a typical temperature curve for human enzymes. Peaks at 37 degrees. Colder temperatures, not so great. Higher temperatures, you get a minor fever, it goes down, you get a severe fever, you die. Because what happens with a severe fever? Your enzymes are denatured. As your proteins are denatured, you die. So if you have like a 1 degree fever, that's okay. That's actually helping your immune system. But if your fever is 104 degrees Fahrenheit, you want to bring the temperature down because you're beginning to denature your proteins. If you look at enzymes from bacteria from hot springs, totally different curve. The optimum is about 70 degrees Celsius. That temperature, you're dead. They're just optimal. And their range is shifted compared to your range. So below 40 degrees, 40 degrees Celsius, too cold for them, so most of the reactions are not happening. And they can tolerate up to 85, 90 degrees Celsius. Not boiling water, but up to that. So something about those proteins are different than yours, even though you all use the same amino acids. Has to be a different arrangement of those amino acids in different shapes that are more stable at different temperatures compared to your proteins are. So your proteins won't work at that temperature, but yours do. pH, same idea. You have an optimum level, and then Gesundheit. Above and below that, the reaction rates go down. But this is not the same reason as temperature. So as you look at pH, what is happening to the solution as pH decreases? More protons. As the pH increases, fewer protons. So as you have more protons, the reaction goes down. As you have more protons, the reaction goes down. So when you have fewer or more, it will affect your protein structure. So let's take a look at why that would be. So I'm drawing an alpha-helix here. And so you have your partially positive partially positive hydrogen on one side that might be joined to a partially negative oxygen on another side of another amino acid. So here's your hydrogen bond, joining a partial positive hydrogen and a partial negative oxygen in this case. What happens if you increase the concentration of protons in the solution? All these extra positive charges in the solution. Yes, sir. The partial negative charge of the oxygen is going to bind to the full positive charge of the proton as opposed to the partial positive charge of the hydrogen on the other amino acid. So this bond formation is going to break the hydrogen bond. What happens if you change the pH in the opposite direction? So here is your partial negative oxygen and here's your partial positive hydrogen. As you increase the pH, the concentration of what increases in the solution? The hydroxide ions, there are more of those. So what happens to the hydrogen bond? Instead of having the partial positive of the hydrogen here bind to the partial negative of the oxygen, this partial positive and that full negative will bind to each other. So that will also break the hydrogen bond. So whether you decrease the pH or you increase the pH, you can break those hydrogen bonds. And so for any given protein, and you look at the shape of the protein and the effect of the pH, whether the pH goes below the optimum or above the optimum. Below the optimum, more positive charges interfering with hydrogen bonds. Above the optimum, more negative charges interfering with the hydrogen bonds. In both cases, you change the shape of the protein, the enzyme doesn't work. And the two graphs you have at the bottom here are both human enzymes. One is from your stomach, that's pepsin, and then trypsin is from your intestine. And they're both involved in protein digestion. But one has an optimum pH of 2, one has an optimum pH of 8. In your stomach, pH is around 2. The acids in your stomach sterilize your food, kill the bacteria to protect your body. The enzymes in the stomach have to have an optimum pH that is in accordance to the acids in your stomach. In your intestines, you add bile. Bile is highly alkaline, so pH 8. The enzymes in the intestine can't be functional at pH 2 because the solution in your intestine is pH 7 point something or 8 pH 8. All right, folks, so we'll